So now let me start off with this following idea that what, how does one use independence? So, so this is the next chapter that I'll go on to now. Second chapter in the book. It's called. It's a very important property in statistics and probability. How to sample? It's called sampling. And the other thing is that it's understanding of independence through repeated trials, or the reverse way. You say you you understand relative frequency through repeated trials, and then use the independence property to understand all this. Okay. Now, so let's consider an event A with sample space S. Now, so you think of an event A as some special event that you're interested in. Let's say you're tossing a coin, and your event A is getting ahead. Okay. So you have S, a sample space, an event space, and a probability P. Let's say. So this is and you have an A is an event of interest, and A subset of S. So A is subset of S. So S contains A. So now the you say you deem two things. You deem it a success if A occurs. Okay. If A occurs in an experiment. And you say define it as a failure if A does not occur. Okay. So your A is your event of interest, and if A does not occur. So what you do is you will conduct experiment. It has many outcomes, perhaps, but you're interested only in event A. A is an event of interest, and you define yourself. You define your whole thing would be say, okay, I'll say A, the experiment is success if A happens. Experiment is a failure if A doesn't happen. So let's just look at a few examples. Let me do a few examples. So let's say the experiment is, let's say the experiment. An experiment. Let's say experiment. One experiment I have, let's say, is I toss a coin. I toss a fair coin. That's my experiment. I could also have an experiment. Let's say I roll a die. Okay, and that's my experiment. Then let's say I my sample space I know exactly. My sample space S I know exactly. So S here is toss. If I toss a fair coin, my sample space is head or tail. Right, that's clear to see. Then if I roll a die, the sample space exactly is 1, 2, 3, 4, 5, 6. What's an event? Let's say the event that I want. Let's say the event A. Let's say that I want. Let's say I want the event is that head occurs. So let's say, and let's say the event A I wanted the roll is, let's say, an even number happens. So the even number happens. Let's say is 2, 4, and 6. Then I know the probability of A in each of these cases, right? So in each of them are equal likely outcome experiments. So each of them. So here it's going to be 1/2. Here it's going to be again 1/2. So 2, 4, 6. So again 1/2. So now maybe I'll just change my event to, let's say, 2 and 4 occurs. So that way it's the difference is a little different. So let's say it's only 2 or 4 occurs is my event A of interest, and that would just mean the probability of A is 1/3. So what you do is you have an experiment with a certain probability, right, of occurrence. So typically what we do is, this is a probability model that you face for experiment. But in applications, what you would do is, you don't know what probability A is. So to estimate that, what you do is you would repeat the experiment many times. and independently. There is one trial doesn't affect the outcome of the other trial, and you would count. You would be interested in the number of successes. And that's what this is what I mean by this kind of if you think a little bit, this notion of repeating experiment many times is kind of sampling from a large population. We'll come to this later on in the class, why this is the same thing. You could intuitively think the following. Let's say you're in a factory that makes pens, let's say, and you want to know if your pen is perfect all the time, your machine is working well. What you do is you produce a batch of 100, you pick one pen at random and see if it's correct. If it's well done, you call that batch success. If it's not done, you call that batch a failure. Right? So and then there's a chance you just see how many times this happens, and then that gives you how well your machine is working, and so on and so forth. And you repeat the experiment many times to get an idea of what the proportion of defects are in your machine. So that's the broad motivation for doing an experiment many times. This is called sampling and repeated trials. So what I'll do now is I'll proceed to give you a mathematical framework for repeated trials. Okay? It does nothing to do with the applications part, but all you know is that the motivation is that you have an experiment that you repeat independently many times, and you count the number of successes to estimate the probability of success, because the relative frequency of success is the probability in an experiment that you conduct. But in terms of a model, I'll try and tell you how to compute probabilities if you repeat an experiment many times. Very good. So these are called Bernoulli trials. So if you're a math geek in high school, you may have seen there's a French I think a bunch of people in the family named after Bernoulli as a last name, who are all mathematicians, and James Bernoulli is sort of credited with this idea of Bernoulli trials. It's around the 17th century. So what here is that this provides a mathematical framework. What I'm going to do is I'm going to provide a mathematical framework for independent trials. Of an experiment and what I'm going to do is I'll designate. So what we do is erase this a little bit. Alright. So I perform an experiment. So it has many outcomes, but I'm interested in a certain event A. So all I'll do is I'll designate the outcomes as two parts: a success or failure. Okay. So then you could think of an experiment having just two outcomes. That means one is success, one is failure. Or you could think of having an experiment many outcomes, but your event of interest is A, and if A happens, you call it success. If A doesn't happen, you call it failure. Very good. And what I'll do is I'll just say I know the probability of success, like the previous the table that I drew for you. So I'll just assume that P is the probability of success. Whatever success is defined to be at each trial. So that's the. So now I could forget about my experiment. I could forget about my larger sample space. I could just fix my sample space to be just success and failure and work with that. So this is what Bernoulli did. This is Bernoulli trial. So this is called Bernoulli P. Bernoulli P. So here I would just assume that instead of many trials, I just say it's one trial. You form a trial. So your trial happens. You have a success or a failure. So your sample space S is just a success happens or failure happens. And we know that the probability of success is P. So this is clear, right? So suppose I take a, why is this enough to discuss the whole sample space? Because I know several things, right? If I have S is given by this, then I know my event space is just empty set, success, failure, the set outcome failure, the outcome success, and the outcome S. That's my event space, right? Because subset of S, only these four guys. And my P is automatically defined from F to 0, 1 because the moment I know success, I know several things, right? Because I know this is automatically probability empty set is 0, that I know. This I know is P by definition. This is failure is the complement of success. So probability of failure is going to be 1 minus the probability of success, which is just 1 minus P. And this we know is just 1. So immediately probability also is very different. So Bernoulli P trials means that the sample space is success or failure and the probability of success is P. Okay, that's the P here. So suppose I say I have a Bernoulli P trial, that means I perform one experiment where the probability of success is P and the experiment has only two outcomes, success and failure. Very good. But often we are interested in how to do multiple trials. But often we are interested in performing multiple trials. In performing multiple Bernoulli P trials. So I'll just call it Bernoulli P trials. Okay, that we understand. That is, we perform an experiment again, and each time the probability of success is P. Very good. So let's see how to understand this. Let's see how does one work with it. So I perform an experiment many times, independent of each other, and the experiment has only two outcomes, success or failure. And I want to know how to perform computations with them. Okay, so let's do this. So let's call this example 2.1.1. Suppose we roll a die twice. So I'll discuss an example where this sort of Bernoulli trials occur naturally. Two times. And my event A of interest, so I'm interested in, let's say, I will not phrase it like the event A. I'll say I'm interested in understanding, I'm asking you a question, how likely is it that we observe exactly 1/6 in the two loops. So this, I don't know if you recall. We did the example before, long time back. So let's say we recall. In example, I think it was 1.4.3. So there, what I did, I said, okay, I have a roll of die 2 times. I wrote down S as my 36 outcomes are there, right? Add 1 1 all the way to 1 6, and then add 6 1 all the way to 6 6. Add mod S is equal to 36. I'd model this like an equal likely outcome experiment, and I describe my event of interest as observing only 1 6. So I say the event of interest is given by only 1 6. That's like 1 6, 2 6, 3 6, 4 6, 5 6 as the event of interest. Another one, right? 6 1, 6 2, 6 3, and so on. 6 5, right? Only 1 6. These are all the possible outcomes that I'm interested in, and I would do that. The probability is mod E by mod S, and the answer would be here. It's just 10 people, right? 1 2 3 4 5, 1 2 3 4 5, 10 by 10. So that's what I did before, right? That's what I did before. But now this is some little cumbersome. This method, let's call this method 1. This is method 1. So the advantage of method 1 is the following: that you're able to prescribe the entire sample space properly. You understand like an equal likely experiment. You discuss your event E of interest in a clear way, and then proceed accordingly. Very nice. But now I don't want to do this. I want to use the fact that each role is independent, and somehow can I use that to compute the question of interest. So what I do is I'm only concerned with 6 occurring or not occurring, right? So what I do now is I see this method 2. Method 1 is this, that I list the outcomes out, I think of it as an equal likely experiment, and I move on. But I can't keep doing it again and again. If I repeat these 10 times, then I don't want to keep doing this. Write the whole 10 tuples, and huge space, and it's just too much. So this is method 2. So I'll try and describe it today, and then I'll build on this when I come next week. So what happens is that here I'm only interested in 6. So what I do is I designate the outcome 6 as success. Okay? So I'll say, let's say, designate 6 occurring in a role as success, and 6 not occurring as failure. In a role as failure. Okay. So this is what I do. I do this terminology. I say fine. So I designate the fact that if 6 happens, I call it a success. If 6 doesn't happen, I call it a failure. So when I do a role, I'm converting it to a success and failure experiment in this following way. So that's how I do this. Very good. Now I do the following. Now I know already that for every single role, it's easy to do, right? I have a single role. Probability of success is, let's say A is the event I'm interested in, that 6 occurs. That is in a role. Right? This I know will imply that probability of A is just 1/6, because in an event that there's 1 through 6 outcomes possible, equal likely, and probability A is just 1/6. And a complement, that is probability of success and probability of failure, as A does not occur, is just 5/6. That's also easy to see. Very good. So now what I do is I go and do the following. This is my event. So what I do is I say A1 be 6 occurs in the first row. What happened now? 6 occurs in the first row. Okay. And I say A2 is the event that 6 occurs in the second row. Very good. I know this. And what am I interested in? I'm interested in 6 occurring in only one row. Right? So now this is what is this is same as saying I already know probability of A1 is 1/6. Probability of A2 is also 1/6. Is also I know for sure. Because each row is independent and just considers only one row. So now I do the following. I remodel this whole thing as a success failure experiment. That's what I'm trying to do. So what I do is I look at this. I look at probability. I have 2 trials now. So one possibility is success and success. Each row I have success in both. This is the same as probability of A1 and A2. We've already seen in the example I did today that A1, A2 are independent. We've seen earlier that A1, A2 are independent. Use independence to get probability of A1 times probability of A2. And that's the same as 1 over 36. Now I also do the following. I do probability of success and failure. What's that going to be? That's going to be probability of A1 and A2 complement. Because that's what failure is, right? Failure means I don't have A2. I don't have 6 in the second row. That's same as again independence again, right? So probability of A1 times probability of A2 complement. So again independence. Shown already. Because we know that A1, A2 are independent, and A1, A2 complement also independent. That's going to be equal to again 1/6 for A1. What is A2 complement? Probability A1 is this, A2 is this. Probability of A2 complement is just going to be 5/6. There's one row. So it's going to be 5/6. So I get 5 over 36. Very nice. Then probability of, then I do the same thing. I can just, let me just, since I'm in iPad, I will do this way. Okay, maybe I'll write it down. So probability of failure and success. Let us fail in the first one is same as A1 complement and A2. That again by independence will be same as probability of A1 complement times probability of A2. That's the same as again 5/6 times 1/6, and that's just 5 over 36. Right. And similarly, to complete the experiment, I can just say that probability of failure and failure, because that's the last event in the sample space that I have to consider, last outcome sample that I have to consider is failure, and that's the same as probability of A1 complement and A2 complement, and that's again the same as probability of A1 complement times probability of A2 complement, and that's going to be equal to 25 by 36. Very good. So in a sense, I've converted my 2 roles because of my question of interest. I've converted my 2-row experiment into an experiment with sample space S as success, failure, and failure, success, and failure. Very good. This is what I did. Event space is just a subset of all this. Anything you want, you take combination. And I know that my function P is f from 0, 1. And I just define it for every outcome. I know the event at success is 1 over 36. The probability of success failure that I computed above was 5 over 36, and the probability of failure success that I computed above was again 5 over 36, and the probability of failure was 1 over 36. And that's enough to give probability, because once I know that the probability of every outcome, the probability of any other event A, we know that let's say any other event A is just going to be the sum over all omega in A, probability of omega. That's how I'll define a probability. So then once this is just a side diversion of how I define my sample space. But let me get back to the question of interest. What is the question of interest? Question of interest was we are exactly 1/6 in 2 rows, right? So that in this corresponding sample space is just one success and one failure, or one failure and success. So that means probability only 1/6 occurs is the same as probability of excuse me, success failure, or make it a little bit smaller. Is the probability of only 1/6 happening occurring, which one interest is the probability of success failure plus probability of let me write it first, union or failure success. That means only 1/6 has happened, and that's the same as the probability of each of them separately, right? Because they're mutually exclusive, and we know each of these is 5 over 36 plus 5 over 36, which is 10 over 36. So it's another way of doing the example. So let me just quickly recap a little bit so that you're sort of on the same page. So the idea was the following: that I had this question that I had in mind. I rolled a die 2 times, and then I'm interested in the fact that only 1/6 happened in 2 rows. So method 1 we had discussed many times before, some days before, right? In which what I did was I laid out the entire outcome space as 36 possible outcomes, and then I wrote down my event of interest, which is 1/6, 2/6 till 5/6, or 6/1, 6/2 till 6/5. There are 10 elements there. It's an equal experiment, so the probability of E was 10 by 36. So this I could do with 2 quite easily. But suppose you can immediately see that it'll get quite complicated if I want to do, let's say, 10 rows, and my event was a little different. Let's say event was, let's say, an even number occurs. It'd be quite complicated to write down the event and write down. So I need a different method to handle this, which I'll discuss next. So it's method 2. So method 2 was the following. So what I did was I said, okay, 6 happens, I call it a success. If 6 does not happen, I call it a failure. So then what happened was, then I know that chance of a failure is 5/6, chance of success is 1/6. That's kind of easy to see, right? Because you're just rolling a die once. If 6 happens, is 1 of 6 possibilities. If it doesn't happen, there's 5 out of 6 possibilities. So it's 1/6 and 5/6. So then I'm in business. Then I look at the fact that I have independent trials. So if I want to compute success and success, I go and look. I say, okay, fine. I have probability of A1 and A2. That means I have independent events. So that's same as probability of A1 times A2. So immediately I get 1/36. So the advantage here was that I used the fact about one trial to get what happens to a 2-trial event. Similarly, success failure I can do the same way. It's just A1 complement and A2 and A1, A2 complement. Again, by independence, I get 5/36. Independence, I get 5/36 and 20/36. So what I have done is I've converted my equal likely outcome experiment. So maybe I should call this S prime. So it's not the same event as before. In some sense, same outcome space as before. What I've done is I've catered to my question of interest, and I've converted my sample space into just success and failure. Okay? And then I know the chance of each success is 1/36, success is 1/36, and so on and so forth, and all outcomes I know. From that, I'm able to compute the probability of only 1/6 occurring, because that's one certainly is success failure and failure success, or failure success, and I get the answer. So in some sense, what I did was, I'll explain this next time, I converted the experiment rolling I had 2 times into 2 independent Bernoulli trials with p equal to 1/6. So I will come and discuss this idea next time, because that's all I did. If you look carefully at what I did, I just converted in method 2, I converted my question, with focus on my question, I converted my experiment into a Bernoulli 1/6 trial, because the probability of success was 1/6. That was probability.